my favorite examples of simple machines in action are the Rube Goldberg machines. And this is probably one of the best ones that I've found so far. What a Rube Goldberg machine is just an over-engineered series of chain reactions that are meant to just complete a relatively simple task at the end. But if you look up Rube Goldberg machines on YouTube, you should find some pretty cool ones on there if you've never looked at Rube Goldberg machines. Of course, the real question I have for these people is who has this much stuff laying around their house in order to do this sort of thing. But obviously today we're going to talk about simple machines. And before we talk about simple machines, maybe we should define what a machine is. And so a machine is any device that uses energy to do work. And remember, we've defined what work is before. Work is simply applying a force to an object over a distance. And so if we had a Coke can here and our Coke can weighed 1 Newton, that would be our force, so we wanted to lift that Coke can a distance of 1 meter off the ground. Well, how much work would we be doing? We would be doing 1 joule of work. And so we can use machines to help us do that work. And we use machines all the time. And usually those are going to be examples of a compound machine, which a compound machine is just a machine with 2 or more simple machines in it. And so we could see that if we broke down our compound machines into the simplest of parts, we would find our simple machines here. And so if we look at the simple machines, there are 6 types of simple machines. And those are the lever, the wheel and axle, the pulley, the inclined plane, the wedge, and the screw. But we can further break down those 6 types of simple machines into 2 main groups, and those are the levers and also the inclined planes. And so you can see I've kind of sorted those out by color here. The ones outlined in blue are the levers, the ones outlined in green are the inclined planes. And so a wheel and axle and a pulley are just modified levers, and a wedge and a screw are just modified inclined planes. And so let's talk about how those are modified inclined planes and levers here. So let's start with the wedge and the screw. They're a little bit easier to think about. The wedge, if we look at what the wedge shape, it's just 2 inclined planes stuck together here. And so we look at the shape of the axe here, it's just 2 inclined planes. A screw is an inclined plane wrapped about a cylinder. And so maybe it's hard to picture by just looking at this little screw, so maybe it's a little bit easier if I could give you an example of a really big screw here. And so what do inclined planes do? They help us get from one level to the next level. And so if we were to sit this big screw up on its end, we would be able to walk up the blades of this screw and get to the next level. And that's sort of like a spiral staircase. A spiral staircase is an example of an inclined plane and also a screw. And so it's just an inclined plane wrapped about a cylinder. Looking at the wheel and axle now and the pulley, those are a little bit harder even for me to picture. How is that a lever? And so I use this example here, and I got this from watching a Bill Nye the Science Guy video. But if we have our lever here and we have with a lever we have a pivot point in the middle, and so that would be right there, and then on one end we have a Coke can attached by a string to one end, and then on the other end we're going to apply our force. So what would happen if we push down on the lever to the Coke can? The Coke can would go up with this side of the lever, right? And so if we took this lever and we bent it upward like this, we would have something that looked like this. Now we have an L-shaped lever. And so we can still do the same thing with this lever. We're just applying our force in this direction now, but what would happen to our Coke can? It would still go up. And so if we took 2 of these levers and stuck them together here, we still have our pivot point here in the middle, we would have something that looks like this. So now you can kind of start to see how this is a wheel and axle or a pulley. And so we can apply our force on any of these levers in different directions here. And what would happen to the Coke can? We'd still get the same thing accomplished. Our Coke can would go up in this direction. So you can even draw a circle around here and see how that looks like a wheel and axle now. So here's our axle in the middle and the wheels around it, and these are levers coming out of the axle there. And so the same thing with a pulley is just a wheel and axle with a rope wrapped around it. So if our rope was going around, we could pull on it and lift that Coke can in the same direction. So this is an example of a trebuchet, and that is a piano. So back to our simple machines. The easiest way to talk about simple machines are to talk about those two main types, so our levers and our inclined plane. So let's talk about the lever first. So the parts of the lever are going to be our arm and then also our fulcrum. And our fulcrum is just the pivot point for our arm. So we can look at any lever and look and see how it magnifies our force, and that's called mechanical advantage. And so if we look at a formula for mechanical advantage, it looks like this. And so if we were to lift an object, wow, that guy's trying to lift the world, maybe it would be a little bit easier if we used a simple machine. So let's put that on our lever here. And so if we were on the other end of this lever, we applied a 2 Newton force on this side, and that would be our input force, or Fi, F sub I. And on this side, using our lever now, it's applying a 10 Newton force on this side to lift the world here, and that would be our output force, or F sub O in our formula here. And so we can look at that and see what our mechanical advantage is. So in other words, a mechanical advantage is how many times it multiplies our input force. So if our input force was 2 newtons, and on the other end we got out 10 newtons of force from our lever, that would be a mechanical advantage of 5. And so it took our input force and it multiplied it times 5, and we got 10 newtons on the other side. And so that is mechanical advantage. Of course, we can't just get the input force multiplied by 5 on the other end without giving something up. So if we look at that on our input side, we have a small force, right? But we have to apply that small force over a greater distance. So you can see that with our arm here, we have a greater distance on this side, and on our output force, we get a large output force, but that's only applied over a smaller distance. So our next simple machine is our inclined plane, and our inclined plane allows us to talk about something called efficiency. So what is the efficiency of our machine that we're using? And so that is work output over work input. So if we had a mass, a ball in this case, and that mass weighed 2 newtons, and let's say that 2 newtons was just too heavy for us to pick it up and put it in the back of a truck here. So what could we do? We could use a simple machine, an inclined plane in this case, and we could move it to the end of our inclined plane, and maybe that would help us load it into the back of the truck. So let's say that using the inclined plane, we only have to apply now a 0.2 Newton force. We're going to move that over a greater distance though, and it's going to be 12 meters. So let's just say that this distance was 1 meter in height. And so to get work, remember that we have to do a force divided by a distance. So let's figure out what our work output is. And work output, you got to think of it as, what are we trying to get out of our machine? Well, really we're trying to get it from the ground level to 1 meter above to the back of the truck. So we would take our force of 2 newtons if we were to do that, 2 times our 1 meter, because that's our distance, and we would get 2 on the work output side. And so that's 2 joules of work. On the input side, what do we actually have to put into it to get it to the back of the truck? Well, it's that 0.2. 0.2 is our force times our 12 meters, and we get 2.4 in this case. So our work input on that side, if we push it up there, would be 2.4 joules. So we're actually doing more work using the simple machine, but we're reducing the amount of force that we have to use to push it up there. And so what do we come up with for our efficiency? We come up with 0.84 on this side. And efficiency is always measured as a percentage, so we have to convert that to a percent, move our decimal place 2 places over, and we have an 84% efficient machine to help us do work. Now, how can we increase efficiency? Remember, one of the things that reduces efficiency is friction. So we can reduce friction and make our machine more efficient. And so we could grease the ramp here and create less friction as we push it up, and that would make our machine more efficient. Now, one thing to remember, we can never have a 100% efficient machine. The work input, the amount of work you put into it, is always going to be greater than what you get out of the machine. If it was 100%, then we would have 2.4 on the work input side, and we would also get 2.4 joules of work out of the machine, but we can't do that. So that was simple machines, and hopefully that was helpful.